Hi, everybody, and welcome to week 3 of Astronomy 120. I know for some reason a lot of you now are probably relying more on the recordings. So I'm hoping that you guys are following, are doing the assignments as you're doing. And I know that a lot of you have submitted those assignments that were due last weekend. And we still have more. Actually, we have a homework assignment that we need to learn also how to do. And this basically covers in a nutshell everything that we will have. I mean, we will have two types of assignments that are coming down the road. One of them, of course, is the midterms and the exams. And the other one is an observation, basically project that you guys need to go outside and collect data and then submit it. So those are all of the different types of assignment that are going to be basically graded on in this class. So this week, the focus is on just one unit, and that is unit 10. In the basically the icebreaker activity that we did, do we live on a flat Earth? That was one of the things that we asked. And of course, the answer is no. I mean, the Earth is not flat. And there are all kinds of reasons for it. Chapter 10 deals with a lot of those reasons. And as you will see, actually, chapter 10 is an old, the ideas are old, basically, in the thousands of years from the time of the Greeks, basically, they were formulated. Some of them were based on philosophical arguments, and others are actually based on observation, that the Earth is round indeed, or spherical in shape, not flat, not any other shape possible. So chapter 10 deals with these things, and also not only they were able to argue the shape of the Earth, but also its size, how big the Earth is, namely its radius. So here is the deal. They not only knew that the Earth is actually spherical shape, but its radius from the center to any point on that sphere, or the diameter, if you wish, which is the distance from one end of the sphere to the other end of the sphere, passing by the center of the sphere. So, and actually, the actual thing that was measured the first time around was the circumference of the Earth. If I were to start walking from this point, not turning left or right, steady still, I will ultimately come back to this point. The question is, how far would I have traveled? The answer, they knew it. It's 40,000 kilometers. So they had actually an estimate of the size of the Earth. Very, very good estimate of the size of the Earth. It's very close from the current number that we know of. And this number, they came up with it about 200 years before the current era. Okay, so this thing is not something that they measured with NASA or something fabricated, as some people speculate, at least on YouTube, trying to gather the likes and followers and things like that. So this thing, it was a known fact. Now, before that, some 200 years before that, some other astronomers, or at least one person, Aristarchus, he was able to estimate the size of the moon if we know the size of the Earth. At that time, he didn't know what the size of the Earth is or the size of the moon. So if we know one, he knew the ratio, and it's 3 to 1. He argued that the size of the Earth is about 3 times the size of the moon. Namely, the diameter of the Earth is about 3 times the diameter of the Earth. But unfortunately, he didn't know the size of one or the other. We didn't know that until about 200 years later, and that is by Eratosthenes, who came up with that estimate of about 40,000 kilometers for the circumference of the Earth. And then, if we go back 200 years before, then we would know how big the moon is, based on that number. Then the same person, Aristarchus, he was able to estimate the distance from the Earth to the moon. And he found it again, not knowing the size of any object, but the ratios only, all he was basically able to deduce, was about 70 times the radius of the Earth. That's kind of a little bit bigger than the current number that we know. We know it's about 60 times bigger. So coming up with an estimate of about 440,000 kilometers versus 384,000 kilometers, I would say it's good for somebody who didn't have any technology or any other laser beams or anything like that to use, based just on geometry and observations. So he came up with a very good estimate to the distance between the Earth and the Moon. He also estimated the distance between the Earth and the Sun, and that was wrong. He came up with about 20 times the size of the Earth. That is not correct. Okay, and I will tell you why that is not correct. Because he made an error. I mean, he did not have access to accurate measurement tools. So he made his best estimate for a measurement of an angle, and that angle he estimated to be, or at least he measured it to be 87 degrees, but the current measurements yield 89 degrees and 50 arc minutes, almost 90 degrees, not quite, but almost 90 degrees. So that's what threw him off. Almost 3 degrees, he was off by 3 degrees. Had he had access to a better measurement techniques, he would also have found the distance to the Sun. That error in the size of the distance of the Earth to the Sun also led to another error for the size of the Sun to the Earth. In his calculations, he came up with a number about 20 times larger than the Moon for the Sun. So he knew that the Sun was larger than the Moon. That's for a fact. He also knew, because of the fact that we said that he argued that the size of the Earth is about 3 times the size of the Moon. Now he came up with the size of the Sun compared to the size of the Moon about 20 times. That puts the Earth almost 7 times bigger. I mean, the Sun 7 times bigger than the Earth. That's his estimates. Today we know it's not correct. The Sun is far more bigger than the Earth is. Okay. Again, that earlier error that he did most likely is the one that led to the second error now in terms of the size of the Sun. But what is amazing then, he was able to find which one is bigger than the other with observation. And because in his estimates, the Sun is about 7 times bigger than the Earth, he argued it does not make sense that the Sun then will orbit the Earth. I mean, the apparent daily motion, it's nonsense that the Sun goes around the Earth. The only way this could be is that if the Earth is actually spinning around the Sun. That was about 400 years before the current era. Some 2,400 or 400 years ago. A long, long time when he came up with that one. However, his idea was rejected, and rightfully so, based on a scientific argument that people, or at least say an observational argument that people made then. That has to do with something we're going to discuss called the parallax. So in his argument, he couldn't really justify the answer to them. So that was disputed. However, his other findings in terms of the ratio of the size of the Earth versus that of the Moon, and in terms of the size of the Sun versus the Earth, and in terms of the distance, those were solid arguments. At least for the size of the Moon, they're actually very good. Others, nowadays we know that he underestimated them a lot when it came to the Sun. He was off by a big factor. And it's because of that 2 degrees and 50 arc minutes that he was off in his measurements of an angle. So it's amazing, really, to see how the ancient did it. And nowadays, we have some lunatics, let me put it that way, who go on all kinds of media and then claim some nonsense stuff. Of course, the motivations are sometimes clear, and many times they hide them. And it's basically just to gather money, to make money, that's all, okay? Just like what the charlatans in the old days used to do. Anyway, so let me share with you the PowerPoints. Okay, before I do that, let me tell you what we have to do this week, okay? And I already alluded to it in the beginning. we have this unit 10, which is a big deal. And because we have a homework on this week also, I mean, it's assigned for this week activities. And I really want to dedicate the next session, which is the Thursday session, on problem solving techniques. Let me warn you ahead of time. I tend to be verbose. I tend to be detailed, okay? And sometimes you might be sidetracked because I'm following an idea. And once I dig into that idea, I usually don't let it, how should I put it? I follow it all the way through, okay? And then I come back to analyze the next point and the next point and the next point. Some of you might find it kind of, okay, we're getting too deep into the idea and we're forgetting something else, so you might be distracted. Please let me know, take notes, and then basically let me know where if you're lost something in here and there. Now, if you're good in problem solving, of course, you're going to pick up on all these things. If you did these things before, especially if you have a lot of math background, you should not have difficulty with these things. One of you guys asked me a question last time when we did that exercise, and that's actually part of the homework that is assigned to. Are we going to have this in the exam? No, this is going to be just for homework type assignments, okay? So that you know. It's not part of the exam. The exam will be basically just the content that we're covering, similar in a sense to the quiz that you already have seen. Okay, so let me share with you the screen. Do you guys have any questions before I do that? No? Okay, so let me share with you the screen. So you guys looking at the screen that I'm sharing, namely Unit 10. And reply in the chat. Okay. Okay, very good. Thank you, Susan. Okay, something happened last week. I don't know if it was a Tuesday or a Thursday, where for some reason my Zoom session basically broke. Please don't leave, okay? So sometimes the internet does that, okay? So because I have so many windows also open, sometimes this computer also tend to shut down and stuff. Anyway, so this is Unit 10, as the title suggests. And I'm hoping that you guys are doing the reading also, which I know a lot of you are already have access to the online resource. And if you're not, you already have the book. So this is the geometry of the moon, Earth, and the sun. So the focus just basically on the geometry. And these are the objectives again, show that the Earth is round and how its size can be found from basic observations. Mr. Pythagoras made an argument based on philosophy, based on his belief that the circle is the most symmetrical shape there is. And since that is the case, anything that is made by the gods, anything that is heavenly, anything that is beautiful has to be spherical because of that symmetry. Okay, everywhere you look at a sphere, it's the same. So that is basically his argument. If you take a cube, for example, or any other shape, or rock, for example, it's not symmetrical. Okay, or at least it has less symmetry. I mean, the cube to some extent has rotational symmetry also. If you rotate it 90 degrees, one way or the other, it keeps its shape. However, the sphere, it doesn't matter how much you rotate it, even with a tiny angle, they're going to retain its symmetry. It looks the same, basically. In other words, tell you, okay, close your eyes, and then I rotate the sphere one way or the other, provided it has the same color everywhere. And I tell you, open your eyes. Did anything change? Did anything happen to the sphere? You wouldn't know. You wouldn't know that I spun it. And if you suspect that, you wouldn't know which direction or by how much of it. So that is the argument he presented. But that's not good enough. Okay? We need something more solid than that. And we're going to talk about that. And actually, it's Aristotle who came up with the sound arguments for that. So again, explain how ancients estimated the size and the distance of the moon. I already talked about Aristarchus and how he came up with those numbers. And then discuss why ancients rejected the Earth, that the Earth orbited the sun. Already argued that Mr. Aristarchus, based on his measurements of the size of the sun and the Earth, he argued that it doesn't make sense that the Earth would, that the sun would spin around the Earth. It's the other way around, that the Earth must be going around the sun. Obviously, his idea was rejected. And there is a solid reason for it, why it was so rejected, okay? Because of course, they didn't have any other estimates. That's one of the reasons. So they had a solid argument. Show us this, we'll agree with you. If you don't show us that, you have no way of, we are not going to follow it. The Earth cannot be spinning around the sun. That's basically the whole point of that. So we'll have to see that. And that is part of the scientific method. That is part of the approach we do in science. If you're going to make a claim based on science, you better back it up by some solid arguments. And I had actually, okay, we're going to talk about that one some other time, but I had a discussion today with somebody on another thing. I mean, he was trying to refute the idea of the existence of God based on the observation of the James Webb, but he was using the same arguments that the people who prove the existence of God, that the God doesn't exist. So if you're going to have, I mean, it's the same thing. So either, since they believe in that, and you believe in something else, then that is your belief and that is their belief. That's a discussion we had today. Again, if you're going to make a scientific argument, that's my point with him too today, you really have to back it up with things that are observable, with things that are measurable. If you cannot do that, then your claim is as good as their claim. And it's not based on science, it's based on something else, which is faith, and that is probably something completely different than what we're doing. So you cannot say science proves or doesn't prove. It has nothing to do with that. Science is a field based on observation. And like in here, Mr. Aristarchus made a claim that here is the Earth must be going around the sun. People came up with solid arguments at that time why that is not the case. And if you want us to believe you, produce this phenomenon. If you cannot produce this phenomenon or show that this phenomenon exists, then your argument is baseless. We cannot take it. So that is how science works. If somebody has a belief system in something else based on some metaphysical things, that is their right. That is what they believe in. The science cannot venture in there and try to make advanced propositions or prove something, because it cannot. It's not its field. So that is the point I'm trying to make in here. So anyway, discuss why ancient rejects the idea that the Earth orbited the sun. And then also, one of the things that we actually, for those sitting in lab, Astronomy 125, which is a lab version of this lab, define the angular measurements. And that was actually part of lab 1 that we did. And we will be relying on this measurement later on for some other stuff. But we will need it also here, especially some assignments down the road too. And that is basically, if you look at an object, nearby or far, it doesn't matter. It occupies a certain space in your field of vision. And that space depends on its actual size, how big the object is. Small object will occupy a smaller space. But then it depends also on its distance, how far away it is from you. And that is very important, because if you look at the stars, they seem like dots in the sky. Some of these are huge. Some of these are big compared to even the biggest things that you know, compared to the biggest thing that you have seen in your life. Bigger than the Earth itself, bigger than the mountains, bigger than your car. Yet if you take a star, your car can easily cover it, or your window or the wall of your home can easily cover that star. But it's much, much, much bigger than even your star, than the sun itself. Why? Because the distance now plays a role. So the angular sizes are important in here. During a solar eclipse, for example, the moon, which we now know is very small compared to even to the Earth, let alone the sun, covers the entire sun. And why? Because it's a lot closer to us. So the combination of these two, the actual size versus the distance, play a role in here. And that is exactly what this thing is. And then we're going to talk about an illusion, called the moon illusion, because sometimes it can be deceiving. Okay? You can look at something and it might be deceiving. If you're driving, for example, or somebody else is driving, of course, you can't do this if you're driving. You have to have somebody else doing it, unless you're backing. If you look at the mountain behind you, and the person is moving away from the mountain, it appears the mountain is growing, getting bigger and bigger as you move away from it, which is nonsense. Isn't it when the distance is further away, the object should appear smaller, yet the mountain, as you move away from it, it appears bigger. Have you guys experienced any of this? At least this issue with the mountain? Anyone to do with it? No? Or you're city dwellers? Okay, very good. At least one person did. Okay, if you did not, pay attention to it next time. We have wonderful mountains in here near San Bernardino Mountains. So if, yeah, okay, very good. If a person is driving and you're looking at the mountain and you're moving away from the mountain seems to be growing in size. That is the illusion we're going to talk about at the end, because it's critical, especially when you're doing measurements for the objects in the sky, especially the moon, for example. It may be misleading, it gives you different perceptions. The moon appears to be bigger when it's rising or when it's setting versus when it's in the middle of the sky. In the middle of the sky, it appears smaller, shrunk in size, but when it's going down or rising just up, when it's full moon, of course, it looks much, much bigger. The moon is really occupying a huge space. And that is the same illusion. The moon is the same size, does not change size. Even if, granted that when it's in the middle of the sky, it's a little bit further away from you by the radius of the Earth, by 6,400 kilometers when just above the horizon. And that's a perception. That's probably, I mean, it appears to be, it's true. I mean, it's further away, but that's not the reason. I mean, 6,400 kilometers is negligible in front of 384,000 kilometers. That's the actual distance. So you shouldn't really see an apparent change in size, okay? It's a good idea to put your name in there because I wouldn't know who you are if you have the phone number, your phone is your name. Okay, so if you're, did you say something? The one with the Samsung phone or Samsung device? No, it's not that close, okay? It's never is close. I mean, it's just a, from your standpoint, it's closer to you from where you're sitting on the Earth, okay? For example, when it's at night and it's a full moon and it's midnight and you're standing just in front of it, that's closer to you than if you are on the other side of the Earth, because the Earth has spun 24 hours from the others by about 12,000 kilometers. But that's your perception only, your position only. For the Earth distance, moon is 384,000 kilometers. Make sense? Okay, very good. Okay, so let me go into the PowerPoint again. Share screen. Okay, so again, as I was saying, Mr. I know I'm saying it with a French accent, so I'm sorry about that, okay? So hopefully you guys correct it. Pythagoras, okay, is the one who made the argument based on philosophy, based on what he believed in, and so on and so forth, without any arguments that the Earth must be spherical. Aristotle made the case for it based on other arguments, basically based on observations. For one of the things, during a lunar eclipse, the shadow of the Earth that is cast on the moon has that spherical shape, okay? If this is where the Earth, okay, and if I have light coming from the other side and here, it's casting shadow that is spherical. But if the Earth is flat, then at some point it's going to cast no shadow, depending on the time of the year and how the Earth is moving, okay, and how the moon is moving. So right now it's casting no shadow if it's really truly flat, or at least it's casting partial shadow, and then it's casting a full shadow. But it always has this spherical shape, okay? It always has this shape, no matter which one. So it must be spherical in his arguments, okay? So that's one of the reasons. The other reasons also, when people are moving toward the south, they could see stars that they couldn't see when they are in the location where they are. So this could only be true if the Earth is actually spherical shaped. In other words, your horizon is limited by where you are. That is your horizon. Then when you move, you have brand new horizon, which give you access to a new sky that you didn't have before. Obviously, the stars that you saw in the old horizon now becomes inaccessible. Like, for example, the second brightest star in the sky, Canopus, cannot be seen in the northern hemisphere. At least for us, you can see it probably sometimes because it's just below it's in the southern hemisphere. But in some part, most of the parts of the northern hemisphere, they cannot even see it. The third largest star also cannot be seen because it's part of the southern hemisphere, which is called Rigil Centaurus. It's coming from the Arabic word which stands for foot. Rigil is foot, and then Centaurus, which is really the centaur, the leg of the centaur. That star also is in southern hemisphere. So that's out of the three largest, the three brightest stars in the sky. We can see Ceres, which is part of part of a big dog. The Canis Major, okay? So that we can see, but we cannot see the other two brightest stars, okay? So that's why, because of our horizon, okay? Because where we are. The fourth one is Procyon. I forgot which one. I know the fifth is actually, no, the fourth is Arcturus, the one that we had in the lab also in physics, in Astronomy 125. That's also the lab, the big deal. And that is actually the brightest star that is seen all year round in the northern hemisphere. So that is actually our star, okay? So we should really be proud of it, because even Ceres, which is the brightest star in the night sky, sometimes we cannot see it, I mean, in the summer, because it's, I mean, it starts to be seen in the summer and ends up, by the end of the winter, it's gone, and then it comes back, because it's not too far also from the equator, okay? The celestial equator. So, and actually it's, again, it's because of this curvature of the Earth. The Earth is spherically shaped, okay? So Arcturus is the fourth brightest star, and the fifth one is actually Vega, which is another big star also that we can see. I mean, that's actually part of the northern hemisphere, okay? So that is the position of where you are. The other argument also that Aristotle made is, if you look at the ship going into the ocean, it starts to basically disappear from the bottom down. And the people who are on the ship looking at the land, for example, tall buildings, they start to disappear from the bottom to coming up, okay? If the Earth were flat, then that should not be the case. They should be probably shrinking in size because you're far away from them, but they should retain their entire shape. Basically, you should still see the base and the top, but that's not the case. We don't do that. We don't see that. So if you see in the picture in here, it has a city. I think this is Lake Michigan and near Chicago. The city starts to disappear from the bottom up because, again, things starts to fall below the horizon. And as you move closer and closer, they start to appear to you. So those are the arguments that were made in the past that the Earth must be spherical in shape, okay? As I was saying, Mr. Aristarchus was the first one who actually came up with numbers. For one thing, he argued the following. Let me see if I can pull my notes in here, because it's a really beautiful argument. I mean, I love it so much. Okay, let me get my pen in here. Let me open one note in here so that you see the beauty of how simple the math was. And this is about 400 BCE when he made this argument. Okay, let me first of all find where it is. Let's start a new page. I'm trying to keep some color coding so that I know what these are. Okay. Shapes. Okay, and let me stop sharing that and let me share with you. Okay, here is his argument. Okay, he noted, I mean, the people before him noted also that the lunar eclipse. We get a color pen. I like. So lunar eclipse takes. Oh no, I don't like that. This color. About 3 hours. It lasts about 3 hours altogether. Okay, for a full lunar eclipse from start to end. From lunar eclipse from start to end takes about 3 hours. Okay, and he basically made the following assumption, that those sizes are actually very close from the size of the Earth. Okay, so it takes about 3 shadows of the Earth to go through the moon during a lunar eclipse. So here is the moon, here is the sun, of course, shining its rays, and here is the Earth when it enters. By the time it leaves, so the whole time from the beginning to the end is about 3 hours, roughly about 3 hours. Obviously, there were different timekeeping. Probably they were using different measurements, but that's fine. Okay, so they had that measurements in there, about 3 hours. Now, you can use it in terms of days. How many that is about what? An eighth of a day? That's fine. It's the same number. So he also knew, and they knew that also, the ancients, that the moon goes from one sign of the zodiac to the other sign, to the same sign of the zodiac in a full cycle in about 27.4 days. That is the sidereal day, if you guys remember. Okay, sidereal lunar month, I'm sorry, that we discussed from unit 8. Okay, so that is not the 29.5. We don't care about that. Is actually the lunar month for our measurements, because again, the Earth is moving, so it needs that extra kick basically to catch up with it. So how many hours that is, if you do the math, 27.4 times 24 hours. So that's going to be, if you pull a calculator, and I really don't know if I have a calculator on this computer, so I'm going to use Excel, okay, because I can do formulas on it. So I'm going to have Excel. So if you have a calculator, just do 27.4 times 24 hours. Because that's how long it takes for one day. You will find that it's 657 hours. That is how much this number is in hours, okay? He approximated it. 657 is approximately equal to 660, okay? This is when you are busy and you don't want to make any kind of precise measurements. This is roughly, he's trying to find an order of magnitude. He was not interested specifically in how big an object is versus another object. So it's about 660 hours. Okay, so here is the deal. Here is the Earth. And here is the moon. It starts full moon. I mean, it starts not full. It starts a new moon, and then it's going to go around the Earth. It takes 660 hours, roughly. That's what that means. A full cycle. Obviously, this is not a new moon because you'll have to wait for the new moon to happen in a year. You'll have to wait 2 more days for the new moon. But the motion, the actual motion of the moon is this exact rotation. Okay. Now this is something to remember. Now the Earth covers about or during the lunar eclipse, about 3 times the size of the Earth. So his question is 660 hours. So this is 3 hours. So the Earth is about 3 hours in these measurements. So he says that the Earth then 660 hours, that is the path of the moon, versus the size of the Earth, which is about 3 hours then the path of the moon, namely this distance as it goes around, the circumference of the path of the moon is about 220. All you have to do is just divide 660 by 3, and that is exactly 200 times 220 Earth sizes. That's the answer. So the moon goes about 220 times 220 Earth sizes. So in other words, take how many Earths you place them in here, it's going to be 220 Earths in this path. That is how much the moon is going to take to go around the Earth. So take 220 Earth, put them lined up one next to one another, and that is how much the path of the moon is. Now here is the thing. If I know this circumference, then I can find this radius, and this radius is exactly the distance to the moon. Why? Because we know that 2 pi times the radius, and the radius exactly is this distance. This is from geometry that they know then. 2 pi times the radius, and the radius is the distance I want to know. So this distance to the Earth to the moon must be this circumference, must be 220 Earth sizes. 220 times Earth sizes. An Earth size is an Earth diameter, by the way, which is twice the radius of the Earth. If you do the math, cancel the 2, divide 220 by pi, it's going to be about 70. Okay, 220 divided by pi. Pi is about 3 point something, 3.14. This number is about 70 times. Isn't this amazing? About 400 before the current era, he had an estimate of how far the moon is from the Earth if he knew what the radius of the Earth is. He didn't know what the radius of the Earth was, but he knows that this distance from here to here is about 70 times the distance from the center of the Earth to any point on the Earth, this radius. Now we know that this radius is about 6,400 kilometers. And we know the distance to the moon is actually 384,000 kilometers. The ratio is not exactly 70, but rather 60 times only. So in other words, he overshot it, but not by much, really. If you think about it, he came up with about 440,000 kilometers, but at that time, nobody had no idea. Is the moon 1 mile away or is it a million miles away? He came up with an order of magnitude. He told you it's about 400,000, and he was not off by that much. And that was a long time ago. So this is really one of the things that is kind of amazing that people have discovered a long time ago. So let me continue with the PowerPoints. I don't know about you guys, but I'm always excited when I go through this thing. So it's so amazing, basically, how much they were able to do. Now, the other thing also, as I was saying, he waited for the moon to be a full quarter, and he reasoned that that full quarter must be a 90-degree angle. So he's dealing with a right angle triangle. And in a right angle triangle, based on geometry, if he can find, since he knows this distance now, he knows one of the sides of the right angle triangle, which is this distance we just came up with, about 70 times the radius of the Earth. Then all he needs is another measurement. It doesn't matter what it is. This is basic geometry from high school geometry, actually. If he knows this angle, or this angle, or this distance, he can deduce whatever you want to ask him about the rest of the triangle, as long as he knows that this is a right angle triangle. Well, he just came up with this measurement about, basically, as I was saying, 440,000 kilometers or something, about 70 times the radius of the Earth. But then he needed to measure this angle, alpha. This is when it went wrong for him. He came up with a measurement to his best of the equipment about 87 degrees. Now we know that angle is actually 89 degrees and 50 arc minutes, practically almost 90 degrees. In other words, the distance to the sun is very, very far away compared to this distance. So that this distance from where he's standing to the sun, or if he were on the moon to the sun, it's practically the same distance. Why? Because this distance is nothing. And this angle, if it's 90 degrees, this is also almost 90 degrees. So that is when he went wrong with this calculation. And he came up with an estimate that the sun is 20 times further away from the Earth, based on this calculation of saying. Based on this argument, also he argued that the sun is about 7 times bigger than the Earth. And that is the extent with which his ability to do the math was. Okay. I think I put him at 400 years. I think it's 3 centuries only, but that's fine. I mean, it's way before any early estimates. Okay, so those are the conclusions. His order of magnitude that the radius of the moon must be the 1/3 of the radius of the Earth is not too off from the current measurements, about 0.27. And his estimate about the 70 times further away from the sun is not really too off compared to about 60 times of what we know today, the distance radii. However, the measurement for the sun is not quite correct. Okay, he made an argument basically that the Earth, since it's smaller than the sun, must be orbiting the sun. People rejected that idea, and here is the reasoning for why it is. And you can do this experiment right now at home, okay? You can close one of your eyes, okay? It doesn't matter which, because you're gonna close the other one. So if you're like me, I'm closing actually the left-hand side, depending on where you're looking. And look at an object far away from you, as far away as you can. And then don't move your head, keep your eye on that object, close your other eye, and you will see it shift. And you will see it shift. I want you guys to do this experiment right now at home. This is called the parallax. Without my eyes sometimes, without my glasses, I'm sorry. So again, here is the experiment that I want you to do. Sit straight from where you are, focus on an object far away from where you are standing as far as you can, okay? Or actually an object close by, it doesn't matter really. And then the close by is not really good, but an object far away, look at it, and you can use two objects, and you will see one of them shifts with respect to the other, okay? So I'm looking right now, I have actually my camera in front of me, and I have a far away object. And then I'm going to do the same thing, and I will see the other object move one way and the other. Did you guys do this? If we're in class, we'll do it together. Okay, this web person is doing it. Anybody else also? Okay, very good. So you guys understand. Do you see it move? Okay, I'm glad that everybody now is on board. Do you guys see the object move one way and the other when you close one eye or the other? Yes? Did the experiment work for you or not? Sometimes it's hard to... Okay, very good. So, okay, somebody is doing it. I'm glad. Yeah, we were creative when we were young. Okay, so this does not require somebody to teach us this thing. I'm glad to hear that. Okay, so this is a known phenomenon. Let me explain it then, what the rationale was. They thought that the stars are somewhat sitting on a sphere, which is called the celestial sphere, okay? And if the Earth was moving around the sun, then faraway objects like this star, for example, and if we are here looking at it, and if the Earth moves around the sun a full half cycle, basically 6 months from now, because we know the Earth goes, the sun does about 12 months around the Earth. So the Earth, if you're saying me that the Earth going around the sun, then it must do it in 6 months to go halfway the other side. Then that star needs to appear on the other side just because of the same phenomenon. This is the parallax. This phenomenon is called the parallax. But hey, we are 300 BCE. We don't see that. Why? Because even the closest star, Proxima Centauri, which you cannot see by your naked eye, with naked eye anyway, but the one that I mentioned earlier, Rigel Centaurus, which is part of the same system, which is actually called nowadays, it has an official name, which is called the Alpha Centauri A, and Alpha Centauri B, which is binary, you can see them just as one star, which is only about 4.3 light years away from it. It's very close. This phenomenon is not easily observable, even with the equipment, let alone with the naked eye. So where they went wrong then was the fact that they did not have sensitive equipment to really measure the parallax. So he was not wrong. Mr. Aristarchus was not wrong, but he couldn't provide the evidence for their argument, because they presented a solid argument. If the Earth were moving around the sun, then this must be true, yet we don't see it. We don't see stars shifting every 6 months from their positions, or every month, or whatever you want us to believe. So this is not correct. And the only reason why they couldn't, it was until like the 19th century when we started really measuring. We had precise enough equipment where we measured parallax. Then at that time, for nearby stars only, the faraway stars, even nowadays, with a more accurate equipment, you cannot measure it. Still too far away to measure any shift in the sky versus the background stars, because of the fact that they're too far to even detect that shift. So this is really the whole point, that really why the idea that the sun must be revolving around the sun was proposed then. Okay. Then came Mr. Eratosthenes about a little later, and he provided the missing link. He provided the size of the Earth. If you know that the moon is about a third of the size of the Earth, then you could tell how big the moon is, because now you know the Earth is, how big it is. If you know that the moon is about 70 times way further away from the Earth as the size of the Earth, but since now you know the size of the Earth, so you can just multiply by 70 and you find how far away the moon is. And this last point I am making in here is critical for Mr. Newton later on, because when he was trying to measure or trying to come up with a law to explain Kepler's laws, he needed these numbers. So these things they have consequences. It's not like they were just basically measured and that's it, forgotten about them. We build knowledge based on that. It was later on Mr. Newton, and he was grateful for the work of these people to build on them and come up with actually more precise theories, and actually more precise, that led to, among other things, for example, the size of Jupiter and how far Jupiter is, and the Earth and so on and so forth, how far it is from different objects. So these things build on each other. So that is part of the scientific process, the scientific method, and people were critical, and rightfully so, and they have presented a solid argument. If you're right that the Earth must be revolving around the sun, then show us a parallax. Obviously, he did not have precise enough equipment to show them that, then he could not. So that's why his idea was forgotten, until it was later on by Mr. Copernicus that he presented other arguments why actually the Earth must be revolving around the sun and not the other way around. Okay. So Mr. Eratosthenes noted that during a time of the year in a city called Sian, which is modern-day Aswan, which is in southern Egypt. If you know the geography of Egypt, near the border with Sudan, just above it, there is a huge lake, which is called after the leader of Egypt in the 1960s. There is the city of Aswan, modern-day Sian. At some point of the year, during the summer solstice, if you put a stick, you don't have any shadow. And if you look into a deep well, the sun is actually, you can see the projection of the sun in the well because it's directly above your head. On the same time of the year, in Alexandria, which is about, I think about 400 kilometers or something from Aswan, a stick will have a shadow. The same time, the same day, there is shadow. And the shadow actually is about 7 degrees. So if the sun is very far away, and he really knew about the work of Aristarchus, okay, so he knows that the sun is very far away. So the rays must be hitting the Earth parallel because they're far away. The source is very far away anyway. So when they come in parallel. So the rays that are hitting us one or cyan are coming straight in. And that's why you don't have any shadow. But in the same time, because of the curvature of the Earth, the rays that are coming straight through, they're actually, and the ray that comes from the center of the Earth to Alexandria, they must form an angle of 7 degrees, and that is the shadow. If you project basic geometry, this line is parallel to this line, and they must be cut by the same line. So this angle also is 7 degrees. So now he has a measurement for this arc sustained between Cyan and also Alexandria, and that angle is 7 degrees. And he knows the distance. He can measure the distance. He can measure it. Basically, you can hire a bunch of people and walk that distance and tell you how big the distance is. Okay, at that time, they didn't have kilometers or meters or something. They were using stadium. How big this in stadii? How many stadia that distance between that city and that city? Well, the arc distance is equal to the angle times this radius, that's all. R times theta gives you the arc distance. Now you know the arc distance, you know theta. All you have to do is divide this arc distance by the angle, provided the angle is not actually in degrees, but in radians. That's it, basic geometry. He came up with the distance for this, the entire circumference and the radius. Can you imagine that this story is about 200 years BCE? This is not in the 1960s fabricated by NASA to somehow, I don't know, some sort of a conspiracy. This stuff is an old documented observations from a long, long time ago. So this is not something that is as this conspiracy is basically come up with. As I was saying, now we have everything we need, or at least a lot of what we think we need, we should have. We can find the distance to the moon, we can find the size of the moon, we can even find the size of the sun, but again, we made a big error based on the observations before they were saying, and we can find the distance to the sun, again, we made a big error for that, but it's still, we have numbers now, okay? It's not scientific unless you express it with numbers, okay? Which brings us to the last point, as I was saying in here earlier, and that is the arc distances, and it's really geometry in here in this case. This is exactly this measurements in here. This is the arc sustained, and this is the angle. The angle and the arc sustained are proportional, or the ratio is equal to this distance. And this is true also in here. This is from geometry. So the size of an object, if you can measure it. So if you take a quarter or a nickel or whatever coin you have access to, and if you move it very close from your eye, you're going to cover the entire room. But if you want to find an object in the room, you can move it just so that it barely covers that object. So if you have, for example, the sun or the moon, it doesn't matter, and you have a nickel, you can bring the nickel very close from you. It's going to cover the entire everything. You cannot see anything because your eye is probably smaller than that portion. But as you start moving it away and away and away and away, at some point you're going to just cover that object that you're looking at. Because if you move it any way further, the object starts to appear on the other sides of the coin. If you bring it further into you, then you're going to cover more than object. So once you barely covered it, you measure that angle. Okay. And if you know this distance, you can somehow find the ratio of this distance to this distance versus the ratio of this object to this object. And that is basically what you can do. The best you can do, these ratios. If somehow you can find the size of this object, you can find its distance. That's the power of this formula. So again, from geometry, the formula is L, which is the physical size of this object, which is its diameter really. divided by the entire circumference. That is what Mr. Eratosthenes actually used, which is from geometry. And this entire difference, the circumference is 2 pi times this radius. And this radius is the distance you're looking for. This must be the ratio of the angle here that you can measure, alpha, divided by 360 degrees. Now, alpha must be in degrees, because this ratio is actually a number, it's in radians. So if you want to measure this angle in degrees, you better divide by 360, and that's where the degrees are coming from. Let me stop sharing, and this is going to probably be the last point in here before we meet on Thursday. Let me share with you another thing in here that I think it's important, and that has to do with the last point, the last objective of this. Let me find it first. Last objective of this chapter of Unit 10. So let me first of all find it. It's under the discussions of this week. So if you go into this week, no, I'm sorry, it's not under discussions. Did I say under discussions? I was wrong. It's actually under the content of this week, week 3 content. Okay. So you go to week 3 content and you look all the way to the bottom. And let me see if I can share with you. Share. Let me close this now and share. Okay. Okay, we're looking at 3 moons, 1, 2, 3. At this point, this one looks bigger, the one that is at the end of the tracks. But actuality, they are all the same size. If you wait, I think I set it up for like half a minute or something. No, not half a minute, 10 seconds or something, 5 seconds. It's going to refresh. At this point, the one that is in the middle of the tracks looks smaller than the one at the end of the tracks and the one that's cut. But in actuality, they are all the same size because the surrounding area amplifies what looks like. And in here, I mean, in your eye, you know how the distance is between the tracks. So if an object fits in it, you think that it's small. If an object covers the entire tracks, you think it's big. That is an illusion. That is in our heads only, okay? That is, but the tracks are actually coming closer to one another at far away because, again, the depth of the distance. That's why the object looks like it's bigger in here, but it is not. So we tend to put things relative to where they are. We know how big the tree is. So our head is making the adjustment already. So if an object appears bigger near that tree, so we assume that it's bigger, but it is an illusion only. So the same thing is true when you're measuring angular sizes, and that is what we were doing earlier, measuring angular sizes. So we tend to look at the moon early when it's rising, when it's a full moon, for example, or it's setting, and we think that it's bigger because it's actually close from the mountains and the horizon. Then when it's in the middle of the sky, it's without any reference to anything. The stars are far away anyway, so you cannot refer to them. So at that point, it's not compared to anything. But when it's close from the mountains, it looks big. The same thing as I was talking earlier about the mountain. As you're driving away from the mountain and you're looking back into the mountain appears to be growing in size. Why is it growing in size? Because the mountain is big. It's big. So when you're moving away from it, it's filling more and more of your window of vision. Because you're looking and the window, there are more stuff covering their window. So it appears to be growing inside, but in actuality, it's not even changing because your distance that you're moved, 5 meters or 10 meters or even half a kilometer is nothing compared to the size of that mountain. So it's really negligible, but it should really be shrinking in size because you're moving away from it. But the reason why it appears to be growing, it's because it's filling more and more of your field of view, and it's giving you that impression that it's growing in size. So that is actually called the moon illusion. And we're going to do observations down the road in this class. So I want you guys to be aware of this phenomenon because this is an eye trick that it can confuse you at times, okay? Any questions about this unit? Okay, as I was saying, this entire module has a lot of stuff in it. I want you guys to really go through it and understand it. And we're meeting on Thursday and it's going to be dedicated mainly to calculations on the homework. Please be patient when you're doing this kind of things. I really want you to take away stuff from them, okay? Part of the learning process is to do things, and I'm sure when you do things, you enjoy them better and you understand them better than if you watch me or anybody else talking about them. And if you're not participating, it's not really as good. Another thing, I was going to send a message about it, but then I did not, is the mission to the moon that was supposed to be launched yesterday. And it was basically they were having problems with the tests of the engine, but at the end they postponed it. I think, what is it, the first when they are going to try again. And this is Artemis 1, the mission to the moon. This is going to be one of the biggest basically project that NASA is taking again to the moon. The reason for it is after Saturn V, this is the biggest basically vessel that they are built to put together. And so this is our basically way of going back to the moon, and hopefully we will have, I mean, the idea is that we will have a manned mission down the road back to the moon. So this mission is just to go to the moon and make some tests and come back again and make sure that we can do that. So that's really what that is. Anybody, do you guys know about this? Are you following it in the news? Okay, very good. Well, then you better, okay, at least one person is, you better go to the news and watch it and Google it, Artemis 1. So it's really a big deal, okay? This is one of the projects of NASA that they've been working on for several years now. And it's actually this week. So let me type what you need to look for, okay? So I'll see you guys on Thursday, unless you guys have any questions. If not, then I'm going to stop the recording. Thank you. Thank you, guys. Thank you very much.